Okay, welcome to GADNEP. So today we have the talk with Andreas Braun, who is going to talk about string compactifications and the arithmetics. Okay, Andreas, go.
Thank you very much, and particularly thank you for inviting me to speak in your seminar. I'm very sorry that I did not manage to join any of the previous talks, because most of them actually seem quite interesting to me, and it's certainly about stuff I want to learn more about. So just to say one word about my background, so I'm a physicist by training. Yeah? So I'm somebody who comes more from a physics background, studying string theory to learn something about the real world, which might be a little bit of a long stretch, but it's still a motivation that you can have. So let me maybe start by, how do I do? There we go. So let me maybe start by giving a little bit of a very general introduction. Yeah. So the kind of thing that people in string theory are usually doing is that you have a string. Can you see my mouse, by the way?
We see, yeah.
So if I can point at things, very good. So in string theory, typically what you have is that, I mean, there's a string, it's a one-dimensional object, but as it flies around through space-time, it sweeps out what is called a world sheet. And you can think about string theory as maps from this world sheet to space-time. And following up on this idea, people back in the 80s tried to see how you can turn this into a consistent physical theory. And they came up with essentially 5 options. They all require space-time to be 10-dimensional, and they have names like to A, to B, and so on and so on. If you want, this is the first moment where some arithmetic enters the game, which is these heterotic string theories, because there part of the data is an even unimodular lattice in 16 dimensions. Yes?
The maps are supposed to be injected. I mean, are we thinking these maps like embeddings of the strings into space-time? Or they may not be injected.
They don't really have to be. But this is just a very general. So this is not something I will use in the following of my talk. So it doesn't really matter for what I will have to say.
Okay, thank you.
But they will generally not have to be. Okay, so what people learned then in the 90s was that these different string theories are all sort of describing the same stuff in various regimes. And that gave rise to such names such as M theory, which is supposed to be described by an 11-dimensional theory in the low energy limit that somehow unifies all of them. And they're related by what I call dualities. So I've written some of their names here. They're called T-duality and S-duality and such things. And the kind of focus of what I will talk about today is what is called F theory. And instead of explaining to you precisely what that is and how that relates this what is called type 2B string theory to this M theory thing here, let me just describe to you sort of the setup or the kind of mathematical data that go into talking about it. Before I do that, let me maybe present you with one more slide about what people typically call string compactifications. So as I said earlier, these strings are supposed to live in 10 dimensions, and then there's also some 11D story going on. And typically, what you might be interested in is some kind of background that is stable in the physical sense. So that means the string propagates there, and the background stays what it is, and it doesn't explode or decay to nothing or something like that. Yeah. So you're looking for specific backgrounds for the string to propagate on that satisfy typically some partial differential equations. And one instance that maybe some of you might be familiar with is the situation where you consider Calabi-Yau manifolds. So Calabi-Yau manifold has a Ricci flat metric, and then this is typically a good solution in string theory. And you might have a background where the 10 dimensions is just like a flat 4-dimensional space. Physics, you have signature 1,3 times one of those Calabi-Yau threefolds. And then you might say, let me look at type 2 strings propagating on such a background, and then you can start saying all kinds of things about the physics and the mathematics of this problem. And the reason I chose this as an example is that that is something that you might be familiar with, because that is the setup of mirror symmetry. And the classical mirror symmetry story, where you will then say, for every Calabi-Yau threefold, there is another one that maybe you call XV like this, such that if I have these two different type 1 string theories on one and the other one on the other, the effective physics is going to be the same. And because the fact that we have this factor here doesn't really play a big role, what people often will say to describe this background here is they will say, I'm looking at type 2A string on a Calabi-Yau threefold X, or I'm looking at type 2B string on a Calabi-Yau threefold XV. So this is just a kind of a jargon that people use a lot. By the way, I'm very open to you asking me questions if something that I'm saying is unclear, or if you want me to go into some more detail with any of these things I'm saying. But I hope this is something that is familiar to you and you've heard people say these kind of words before. So now let me come to this F-theory thing. So instead of explaining to you the history of this and why people think that makes sense, let me maybe explain this to you a little bit as a setup plus, so kind of defining data plus physical consequences. So in F-theory, the kind of objects you're interested in are not Calabi-Yau threefolds, but Calabi-Yau fourfolds. So a four-dimensional, projective, Kähler variety that has a vanishing first-term class. And that's not the whole story, but furthermore, what you want is you want this fourfold to have an elliptic fibration. So there's a map from this fourfold to a complex three-dimensional space B, that is the base of the elliptic fibration. And if you want, you can think about B as something as CP3 or something like that. Maybe some Fano variety might be nice. And furthermore, you typically assume that there is a zero section of this elliptic fibration. So you can write down a sort of Weierstrass model if you want. And crucially, if you have that, there will be loci in the base, divisors of the base, where the elliptic fiber will degenerate. And because the base is complex three-dimensional, such divisors can intersect. And you can draw a picture such as the one that I've drawn here. So this red thing here is supposed to be one component of the discriminant, and maybe this is another one. And that has a very, very clear physical meaning in that it tells you about degrees of freedom in the sort of effective physical description. So although the defining data is this stuff here, sort of the output data would be physics in 3+1 dimension. And something that physicists are typically very interested in because it has a big relevance in our description of particle physics, standard model, are what are called gauge theories. Gauge theories are, in simple terms, I mean, well, if you want, there's fields in your theory that are connections of some principal fiber bundle. And you're interested in which structure groups you can have and all of that. And that's sort of encoded in the generations of the fiber here, because you see these degenerations here that happen over divisors essentially fall into this kind of Kodaira classification here. So they have names like IN star, and so on and so on. And they have a nice correspondence to simply laced Lie algebras. And somehow for physics, if you give me one of those models, one of the first questions I'm going to ask you is, what kind of singular fibers do you have? What kind of singular fiber types are going to appear? How are they going to meet? Because that will allow me to extract the effective physics. So the details of that are really not important. The crucial point is that this is something that I would be interested in, and I might even be interested in making specific geometries that have specific features like that. So this is not the whole defining data. So it's not just geometry, but there's more stuff. And that's where things get a little bit more interesting. And that stuff is what physicists often call a flux. So you can think about this as a four-form. And people often call it G4. So the 4 is because it's a four-form on X. And that has to satisfy a bunch of that has to have a bunch of properties. So first of all, it's supposed to be, so there's a little caveat here, but let me maybe forget that for the time being. First of all, it has to be in the integral fourth cohomology. Yeah? So you might say as a physicist, this is a sort of quantization condition. And the second property is that this thing has to be of Hodge type 2,2. And one way you can say why that has to be the case is supersymmetry. So that means that this thing has to be a Hodge cycle. So this is already something that I hope is interesting to mathematicians. And okay, so now these are some of the first requirements. And then there's a requirement that you might say is a consistency requirement, or maybe you can also rephrase it as a stability requirement in physics, which says that the square or the self-intersection number of this four-form or of the dual cycle is, or 1/2 times that, is less or equal than the Euler characteristic of the Calabi-Yau fourfold divided by 24. So just picking something that satisfies this first constraint, quantization and supersymmetry, as I wrote, that is not enough. It has to satisfy this bound. And that is certainly something that is going to be interesting to us. There's a little bit of fine print here. It has to be primitive, and it has to somehow play with the elliptic vibration in the right way. But let me go over that, because it will not really play a big role in what I'm going to say. Maybe the kind of take-home lesson might be, if I tell you that you want something integral or some Hodge cycle, you might just say, hey, let me just take the intersection or the dual of the intersection of two divisors. That would be a very easy choice that would satisfy this requirement. But that is not really what you're interested in. And the reason is the following. What you're somehow interested in as a physicist is the following problem. So if you have a Calabi-Yau fourfold, then of course there's a Ritchie-flat metric, and you want to choose this Ritchie-flat metric as part of your geometric data. I mean, you don't have it explicitly, but you don't really care about that. And of course, there are deformations that will keep the metric Ritchie-flat, and they fall into two classes. And one of them is what I call complex structure deformations. And they are in one-to-one correspondence to 3,1 forms on this Calabi-Yau fourfold, which you can represent as a sort of covariant derivative acting on the holomorphic 4-0 form that you have on a Calabi-Yau fourfold. And of course, if you pick a Hodge cycle, then there will be a Hodge locus. So not all deformations will keep this Hodge cycle of type 2,2. And that is really what is interesting to you as a physicist, because you're going to say, so I have all of this defining data of my background here. And once I have chosen it, some complex structure deformations will be obstructed. Because if I do deform in the wrong directions, then this four-form ceases to be of Hodge type 2,2. And there's, of course, a whole physics story there. There's, if you want some kind of potential function that a solution has to minimize, and if you pick the wrong deformation, then you move away from the minimum. And of course, now you can go and you can work out what is the dimension of this Hodge locus. So what you want to do is you want to compute the rank of this matrix here. And what you want typically is for that thing to be maximal. So what you want is you want to have a situation where all your complete geometry is rigidified. So we could now have a whole story why that is physically interesting and relevant, but I'm not going to do that. I'm just going to say this is the kind of thing that many people, including myself, are interested in. And so kind of big header I could put over all of this now is I could say, how can we understand the structure of such solutions or of such backgrounds? Yeah. So all of this stuff here, Calabi-Yau fourfold, maybe with an elliptic vibration, some four-form such that the Hodge locus is a bunch of points, zero-dimensional. And my fourfold is completely rigidified. All right. Can I answer any questions at this point before I go into some more detail and discuss some more examples?
I mean, in the previous slide, there was last condition that you put. You explained this has to do with Hodge locus because I don't understand. In the previous slide.
You mean the fine print?
The G4 wedge J equal to 0 and so
right. So the G4 wedge J equal to 0, this is like primitivity. No, so J is supposed to be the Kähler form. Sorry.
J is the okay.
J is supposed to be the Kähler form. So this thing has to be precisely yes. And then dA and dB, these are supposed to be divisors of the base. And of course, I can just lift them to the whole elliptic fibration, so they become naturally divisors on the fourfold. Sigma naught is the 0 section, and I want these things to be orthogonal. Yeah, so this means that if you just take G4 as a intersection of divisors, then you have a danger there. But if it's not, then there's no problem with these conditions.
So in any case, G4 is orthogonal to all Hodge classes coming from the divisor, something like this, no?
Well, it doesn't have to be. Yeah. In some sense, it's yes. In some sense, it's orthogonal to Hodge classes that come from the base.
Okay.
Yeah. So the only divisors somehow G can speak to are somehow divisors that have to do with reducible fiber components of the elliptic fibration. But anyway, this is like a detail that will not be really important. But I didn't want to somehow. I didn't want to omit these conditions because they're quite important physically. Okay, so the general question I'm after is how can I understand such things? How can I make nice examples? And how can I try to understand how many solutions there are or not? And the kind of reason I put arithmetic in the title is the following. So people have asked this question already some time ago. And people typically ignored the kind of integrality, the arithmetic bit of the problem. So people would say, look, we have these fluxes, this G4. Let me just forget about the integrality for the time being. And let me make estimates for what kind of solutions I can have and how many we have. And people would then come up with statements such as there's 10 to the so many 100 or 1,000 solutions to this problem, roughly. And you can essentially do whatever you want to do. And I don't think, and many other people might agree with that is completely true. But of course, it's also excusable to speak like this because it's very, very difficult to solve such things explicitly and to really work out solutions of that type. So let me maybe explain a few kind of setups in which people have made, including myself, have made some progress on this, and where we can say something and we can see some kind of pretty things emerging. So the first example I want to speak about are K3 surfaces. So if you want to have a Calabi-Yau fourfold, a kind of slightly degenerate but simpler example would be a product of two K3 surfaces. So we can take a product of two K3 surfaces. That's going to be a Calabi-Yau fourfold. I will call it X, and I will call the K3 surfaces S1 and S2. So just as a reminder, K3 surface is a Calabi-Yau manifold in two complex dimensions. If you want, it's the only non-trivial one that there is. And well, the second Chern character is even. So remember, there was this quantization condition here. So this part, the C2 is even. This doesn't really give me any non-trivial contribution, so I can forget about it. The other characteristic is 24 squared of that background. And now there's a very beautiful you might say, set of solutions where, in fact, all of the complex structure is completely stabilized. So the Hodge locus is, in fact, zero-dimensional. If you can find a complex number gamma such that this object here is, and here there should be a comma z, I'm sorry about that, such that this is, in fact, integral. Apologies for this omission. That's a rather crucial one. So this solutions are already quite old. They appeared in a paper by Paul Aspinwall and Renata Kalosh in 2005. And the really beautiful consequence of this, by the way, omega 1 to 0 and omega 2. So and there should be a 0, 2. Sorry, because it's the bar of the 2, 0. So it's a 0, 2. These are the holomorphic two forms of these two K3 surfaces. And the beautiful thing is that this implies that both of these K3 surfaces are singular, or as some physicists like to call them, attractive, because as manifolds. I mean, they're not singular varieties. They're actually smooth. But the singular means special here. And they're special in the sense that the Picard group, so the intersection of the 1-1 cohomology with the integral second cohomology is maximal. And maximal here means having rank 20. So these are very, very special and beautiful things that just happen from asking to have a solution where everything, all the complex structure, is stabilized. And you can understand it. I mean, the second cohomology of a K3 surface is 22-dimensional. So if this is the Picard, if the Picard lattice has rank 20, then there's only a 2-dimensional subspace for the holomorphic 2-0 form to live in, and that completely fixes it. Well, or that rather puts it in a 0-dimensional locus, I should say.
So if the statement is that if gamma exists, this number, then the surfaces are necessarily singular, no?
Right.
Yeah.
So there's precisely. So if gamma exists, then they're singular in the sense that the Picard rank is 20. Yes. And there's a few more things that happen now. So of course, if you hear singular K3 surface or attractive K3 surface, of course, there's a famous classification result by Shioda and Inose that says these things are in one-to-one correspondence with a quadratic form modulo SL2Z. And one of the kind of implications is easy to understand. There's the H2 of the K3 surface over the integers. There's the Picard lattice sitting inside of that. That is rank 20. The orthogonal complement is a 2-dimensional lattice. And that thing here is the inner form on this 2-dimensional lattice. The converse, that given such a form, there is a corresponding K3 surface, is harder to show. And I think that was the crucial work of Shioda and also where they had some clever tweak of a Kummer construction that would show this. And now, given two attractive K3 surfaces, so we need first of all, or two singular, first of all, for this to be integral, we need both the K3 surfaces to be singular. Again, in the sense Picard rank is 20, and we need the product, the determinant of the product of these matrices to be a perfect square. Now, these quadratic forms are associated with imaginary quadratic number fields, and saying that the determinant of the product is a perfect square just means that these are the same number fields. So it's already quite beautiful, the kind of structure we get here. And now, now remember that there was this, what I call tadpole constraint. So this constraint that the square of this 4 form was bounded. And together, that actually implies that there are only finitely many solutions to this problem. And you can make a list of all of them if you want. So for example, if I want to have this inequality saturated, this is the complete list of solutions where these labels A, B, C, D, E, F label these binary quadratic forms of these two attractive or singular K3 surfaces. Okay, so now if we're doing F theory, I told you that there's this crucial ingredient which is an elliptic vibration. And furthermore, we're interested in what kind of reducible fibers do we have on this elliptic vibration, because that teaches us something about the physics.
Just one question.
Yeah, yeah.
Gamma upper something means that you are not able to compute gamma, or what it means?
No, sorry. So these are just six roots of unity.
Six roots of unity. Okay.
very, very, very simple. Sorry, very, very simple. Very, very simple. Very, very simple.
Okay.
Yeah. The thing is, if you work out this object here, I mean, you can just write this object here in terms of this determinants D and in terms of this number gamma at the end of the day, and then you see that essentially, for these solutions here, these numbers, D1 and D2, they have to divide 24. And then you find somehow the gamma is some corresponding nth root of unity. So it's either like a 6/4 second or root of unity for all of these cases. Yeah, it's very simple. It's nothing too complicated. So something that I've worked on some years ago that was then interesting. I mean, this is a very beautiful setup where you can really say what your solutions are like before you remember that in F theory you want to speak about elliptic fibrations as well. So you're asking yourself, these solutions, do they have elliptic fibrations? Yes or no? And that question can also be answered. And it can be answered in the affirmative. They do. Actually, all of them have elliptic fibrations. And the reason you can conclude that is that there's a very nice theorem that follows from the Torelli theorem, and I think it's already explained in this paper by Pedayevsky, Shapiro, and Shafarevich, which is that if you have a primitive embedding of a copy of the hyperbolic lattice U into the Picard lattice of a K3 surface, then that fixes an elliptic fibration for you. Again, the hyperbolic lattice you can think about as containing the base and the zero section and the fiber of this elliptic fibration. Again, it's a little bit more difficult to show the converse, but okay. And given such an embedding, something that you can work out is what is called the frame lattice W. So what you do is F is supposed to be the class of the fiber of this elliptic fibration. And you can look at its orthogonal complement in the Picard lattice modulo the class of the fiber again. And that gives you a lattice. And because in our case, because U is a even and self-dual lattice, and if you embed an even self-dual lattice into something like the Picard lattice, then and you work out the orthogonal complement, then it turns out that the Picard lattice, or generally any lattice that you embed such an even unimodular lattice into, actually splits as a direct sum, or is isomorphic to a direct sum of this even self-dual lattice, which is in this case the hyperbolic lattice and this frame lattice. And morally speaking, you can think about this frame lattice as having components of reducible fibers and the model Y group, so the group of sections of this elliptic fibration. And given such an embedding and given such a frame lattice, you can of course look at the root sublattice of this frame lattice, which are just the elements that square to -2. And a junction, you can see that for a K3 surface, if you have some irreducible curve, algebraic curve that squares to -2, then that is a P1. So that makes perfect sense. And you can think about the root lattice as telling you about components of reducible fibers of the elliptic fibration. The reason that is an interesting thing to look at is that, as I said earlier, as a physicist, you're interested in these types of reducible fibers because they tell you something about the physics that you're actually describing with this kind of model. Yeah? So if you can work out this W root lattice, then you understand something about the physics. And of course, that now depends on which kind of embeddings into these Picard lattices we are choosing. And there's a very, very beautiful method for working that out due to Knese and Nishiyama. So what you do here is you look at the discriminant form of a lattice, which is just the discriminant group is just the quotient of the dual lattice by the lattice itself, and that inherits in a form that's called the discriminant form from the lattice L. And now there's a bunch of very beautiful theorems that tell you about how these discriminant forms behave if you have a situation such as here, where you have a direct sum of two lattices embedded into another lattice. In particular, if that lattice was unimodular, then these would have to have the same discriminant form. Well, which it is not in general. But the point is that the Picard lattice has such a discriminant form. And of course, its orthogonal complement in the second cohomology is the transcendental lattice. And the second cohomology is an even unimodular lattice for a K3 surface. So then there's a theorem that tells you that these discriminant forms have to be the same up to a sign. And the trick of the Kneser-Nishiyama method is to say that if we had an elliptic vibration on a K3 surface, so we had this embedding of U into the Picard lattice, and the Picard lattice would split in this way, then of course the discriminant form of the Picard lattice is the same as the discriminant form of the frame lattice, because this summand is even and self-dual, so it doesn't contribute anything. And if we had a six-dimensional lattice that had the same discriminant form up to a sign as this frame lattice of some elliptic vibration, then there must exist by an embedding into one of the Niemeyer lattices. So given such a six-dimensional lattice, T with these properties, I can just study all of its embeddings into the Niemeyer lattices, or the 24-dimensional even unimodular lattices, and I can find out all possible frame lattices for such elliptic vibrations. And now there's methods, well, you can essentially use the same tricks again, because the discriminant form of this must be the same as minus the one of this, and so on, until we arrive at the discriminant form of this Q. Remember, Q was this binary quadratic form that gave us this transcendental lattice of these attractive or singular K3 surfaces. And if we, well, this is something that will be positive definite, and typically here you will use this to be a negative definite lattice, because that's the kind of convention that appears in geometry. And you can show that you can always embed these binary quadratic forms into the E8 lattice, and that's how you can get these T-knots with the prescribed properties, and that's a method you can use to classify all of these elliptic vibrations. Can I answer any questions at this point? I hope I didn't go too quickly over all of this.
Maybe this the zero section and the fiber, their cohomology class, it is in F or in the dual of F that you started with? You started in your previous...
Yeah, you mean this slide?
Yeah, I mean, you said this Piatowski-Shabiri implies that at the end there is some elliptic vibration. This has zero section and it has, let's say, the cohomology class of the fiber.
Yes.
They fall in F or in F orthogonal?
No, so F is really the fiber class. F is the class of the fiber of the elliptic vibration.
Right? Okay.
Right. Because the fiber is an elliptic curve, so it squares to zero. Of course, it's also a fiber, no? And intersects the base once. And the base, or the section, zero section, I should say, is a -2 curve, no? It's a P1, so it squares to -2. So you get a little intersection form, and that is equivalent modulo SL to Z to this lattice U. So you can think of U as being generated by these guys. And then everything that's perpendicular is this frame lattice, right? That tells you, are there more divisors? And what are they like? Okay, so this is the complete set of kind of labels of these singular K3 surfaces appearing in this problem. And it's an open problem to find all of the elliptic vibrations of all of these. So, and the reason that is interesting, I mean, of course, mathematically, you might just say, okay, fine, why not? I mean, people have done these kind of things and classified these kind of things in the past. But what is interesting here is that this would give you a complete list of all of the kind of physical models that appear there. Or rather, it will give you it will allow you to understand specific features of all of these models. And the interesting conjecture is that I came up with is that all of the root lattices that appear here, all of the root sublattices of these frame lattices that appear here should always be non-zero. So that means all of the elliptic vibrations on these singular K3 surfaces should have reducible fibers. That's, of course, generally not true. It's easy to come up with examples of attractive or singular K3 surfaces that have elliptic vibrations that are not of this type. But crucially here, and that's one of the things that I'm interested in understanding, is that this bound, how this bound is what somehow gives you only finitely many solutions to this problem, right? Without this bound, of course, this setup here, there would be infinitely many things that you could consider, but this bound brings you down to finitely many. And one question that you can ask is, are they special in some sense? And I think for these ones, they are special in the sense that I can study all of the elliptic vibrations on these things. I can work out the frame lattices. I can work out the root sublattices of those. And I think they should always end up being non-trivial. And one kind of should I say, evidence I have for this is rather weird. I worked with this with a student some time ago. And while we didn't prove anything, what we figured out is that if this conjecture was wrong, there would be a new record sphere packing in 18 dimensions, which would be equally surprising if that existed and you would find it in this way. Okay, so let me not maybe go through the details of that, but let me back up a little bit and let me somehow zoom out and come back from this K3 story. So the punchline here is that if you look at this kind of problems, if you look at this general F-theory setup where you have these elliptically fibered Calabi-Yau fourfolds and you have these Hodge cycles, and you're asking about the properties of that, we found something rather pretty. You know, these two K3 surfaces are singular. They're described by these binary quadratic forms. We have these number fields flying around, and you might wonder, can something like this be true in more generality? Is there a more general story that connects these kind of F-theory solutions with fluxes to arithmetic? And in fact, if you look in the literature, it's a bit sparse, but again and again, people have conjectured such things or come up with such ideas. So this paper here by De Wolf and company, that's already from the, you might say, early 2000s. They already had the idea that, look, on general grounds, you would expect periods for such solutions to take values in some number fields. And what they considered were situations where you have a Calabi-Yau threefold times an elliptic curve as a fourfold. So again, a slightly degenerate situation. And that idea was taken up by Kaita Kano and Taizan Watari, who looked at orbifolds of such things. So you can have a K3 surface. So these are like models for this Z here. K3 surface times an elliptic curve modulo some involution that respects the Calabi-Yau structure, or rather you can have fourfolds like the ones we discussed before, and you can quotient them by some involution. And they come up with a similar story that is rather lengthy, and I will not be able to do justice to it, so let me not say much more than that. And furthermore, there's another observation that you can make, which is that these attractive or singular K3 surfaces that appear here, they are all modular, which has been known for a while. So there's this absolute Galois group that acts on the second Détail cohomology of these things, and it splits such that there's a two-dimensional representation, which is responsible for this modularity. And there's a similar story for what I call rigid Calabi-Yau threefolds. So these are Calabi-Yau threefolds where the middle cohomology is purely of Hodge type 30 plus 03. So there's nothing to be split here because that's all there is. And furthermore, recently there were two papers, again by some physicists, that there might be a more general relationship of modularity of fluxes, not just to maybe some number fields flying around, but to actual modularity. And they also looked at Calabi-Yau fourfolds that are products of Calabi-Yau threefolds times elliptic curves, or at least that's one way to write them. So what I want to speak about in the remaining time is sort of honest Calabi-Yau fourfolds. So Calabi-Yau fourfolds are not just products or bifolds. And the kind of thing I want to talk about is the sextic fourfold in CP5. I mean, that thing doesn't have an elliptic vibration, but it's a simple example to get started and to try to understand or try to learn something more general about such questions. So let me be a little bit more precise. So we can write the sextic fourfold in such a way. So I take some homogeneous polynomial of degree 6 in CP5, and there's a bunch of coefficients phi I. In fact, there's 426 of them, 426 inequivalent of them. And if I vary them, I vary the complex structure on this sextic fourfold, and you can easily work out some topological numbers of these things. And the kind of question I want to ask is that, okay, let's fix these things somewhere and try to see if once I've done that, I can find a four-form that is, sorry, that is not the way it's supposed to be written. There's supposed to be a cap there. Sorry about that imprecision here. So can we find some four-form flux that is of Hodge type 2,2, that is integral or rather appropriately quantized, such that the rank of this matrix that tells me about the dimension of the Hodge locus is maximal. And furthermore, and that's where things get a little bit more interesting, what is the shortest such four-form I can find? And it doesn't satisfy this bound that is imposed on me by the physics. So these are questions that again, I have had in my mind for a long time. And this is probably might be the easiest example in which you can study it. And finally, you can ask about this whole arithmetic modularity story. Does this have anything to do with modularity, and can we learn something from that? So something I did with collaborator last year, again, following up on an idea that we had for a long time, and that I hope is something that appears natural to you, is to say, well, if you want something that is of Hodge type 2,2 and integral, you might just look at an algebraic cycle, because they are integral by construction, and they're also of Hodge type 2,2. So that's very, very nice. And of course, for this sextic Calabi-Yau fourfold, you can easily assume that it has some factorization like this, and then you can find an algebraic cycle associated with that. And you can work out, in this case, that this will sort of fix for you 19 complex structure moduli. Furthermore, it's known, I think, from work by Aoki and Shioda, that for the Fermat quintic, in fact, over Q, H22 is completely generated by such algebraic cycles. And of course, at the Fermat point, you can write down lots of these things. And I learned some of these things after going through some of the old papers by Aoki and Shioda. I discovered Hossein's work on these things and his nice review. So that was very, very useful for me to learn some of these things. And in particular, in some paper with Loyola, they worked out these periods. So if you take the residue form, you can represent the whole middle cohomology with such residues, and then you can try to integrate them over these algebraic cycles. And if you know these periods, then you can completely work out the rank of this matrix that tells you about about how many moduli sort of are fixed. What is the dimension of the Hodge locus? And now, of course, let me come back to these questions. Let me look at the first question again and try to see if we can say something about that. And well, it's rather difficult, of course, because there's lots of cycles flying around, and of course the linear ones aren't the only ones, and all of that. But what you can do, or what we did, is you can sort of have a semi-systematic way of trying to find what is called a general Hodge cycle. So a Hodge cycle where the Hodge locus is zero-dimensional. And you can very quickly see that, I mean, because if you have one of those linear algebraic cycles, that's going to sort of fix, let me use this language, fix for you 19 complex structure moduli. There are 426. So that means if they would sort of be independent, you would at least need to have a linear combination of 23 of them. And it turns out that 23 are indeed sufficient, and we found a specific or several sets of 23 such linear cycles where you just take a linear combination with plus or minus ones that do that for you, that give you a rank of the full rank or the maximal rank, possible rank of this matrix, that tells you how many complex structure moduli are fixed. And the kind of way we did that is you observe that sorry, this is supposed to be rank mu and not rank Gij. That you observe is that depending on the intersection number of two of them, which can be either 0, 1, minus 4, or 21. It's 21 if you actually have twice the same thing. And then, of course, the sum fixes as many complex structure moduli as one of them would. But that, so if they intersect with minus 4, that's the case where they share a line, so to say. They sort of share 6 of these things, so that together they only stabilize 32, or together, I mean, I just take the sum of them. And whereas if the intersection number is 1, they're in this sense independent of one another. And so you can just try to find as many independent ones as you can get, or you can try to find 23 independent ones. And then you can check using the periods that were computed in this paper that the rank is indeed 426. However, the kind of shortest one, what we did is just some kind of as I said, semi-systematic construction with some randomization and computer searching, but it's of course not an exhaustive search. And in particular, we just used the linear ones. We just used the linear algebraic cycles, and we found that the square of this 4 form is in fact always bigger or equal to 775 over 4, whereas the bound that the physics tells us is that this is supposed to be smaller or equal to the Euler characteristic divided by 24, which is 2610 over 24. So you see, this is like a little bit more than 100, and this here is a little bit less than 200. So that's pretty bad. So this is like almost a factor of 2 too much. And now you can look at these nonlinear complete intersection algebraic cycles, and you can try to use them. And there I didn't implement any search, but if you try to use similar ideas, you end up with the estimate that you will find something similar. You will, of course, be able to find a general Hodge cycle, but the kind of the length of this 4 form will be too much. So let me come back to these 3 questions that I was asking. So the answer to the first question is, of course, yes. And this is, I think, something that is well known, that these things exist. And I think that's also something that if you look at Hossein's notes on Hodge theory, this is already very clearly stated there, that such things should exist. But the second question is still pretty open. What is the shortest such 4 form? And is it true that it satisfies this bound? And I have the feeling that that's not the case. And that would of course, be super interesting for physicists, because it would show you that the kind of setup that you're looking at is much more restrictive than people would naively think once you properly take into account that what you're dealing with here, all of the things you're dealing with here are integral. And it would be amazing if one could do such a thing, even though it would just be for the, I mean, physicists are typically interested in gazillions of different Calabi-Yau fourfolds that you can construct in all kinds of ways. And of course, there's lots of different points in the moduli space of this sextic fourfold you might look at. But even if you just look at the Fermat sextic fourfold, and you can show there that that the shortest four-form that has a Hodge locus that is zero-dimensional is such that it violates this bound, that would still be super, super interesting. And of course, that's a task that requires quite a few things. If you want to use algebraic cycles, then you would first have to prove the Hodge conjecture over Z. And then you would have to find an efficient algorithm to really systematically find such a shortest G4. And I don't quite know precisely how to do this at present. But that's certainly an interesting research problem that I want to look at in the future. And finally, let me say something about modularity, because there were recently some papers that in fact claimed that the Fermat sextic also is in fact modular, and that is related to a new form of weight 5 and level 432. So I wrote evidence here because, so this appeared in a paper by Wenze Yang from I think 3 months ago, because I don't think the paper is completely conclusive on that matter, but it's certainly a very, very interesting idea that I think ties in with the general question about the relationship of arithmetic, number fields, modularity, and these F-theory flux vacua. And the really open and interesting question here is this something, is this point of view something that we can use? Or is there some relationship between arithmetic or modular properties and the existence, non-existence, minimal length of such four forms that give you a Hodge locus that is zero-dimensional? All right, thank you very much. Let me start. Yeah.
Okay, maybe let's thanks. Okay.
Sorry about that.
Okay. Actually, I have many questions. Let's the recorded session. Somebody has any question? Let me first ask the audience. Okay, maybe just in the recorded session. I mean, does somebody has tried to find for CM abelian fourfold this kind of flux or Hodge cycle? Because in the mathematics literature, first we have the examples of Hodge cycles by Mumford around 1960s and underway, and this has been very classical Hodge cycles, yet we don't know Hodge conjecture. And mathematicians usually try to solve your problem starting from abelian fourfold, not but abelian, but Calabi-Yau fourfold.
I think people have done that. I mean, so it's because they kind of, okay, so I think in physics language, people would just say, okay, these are just products of tori. Or like a simple version of that would be products of tori. And this is, of course, things that people have, in fact, looked at, yes. I think so.
Yeah, but the existence of this flux, is it?
Yes, no, I mean, I think there you can find solutions that stabilize everything and it exists. I think there it's fine. But otherwise, these are a little bit, I mean, from the point of view of physics, these are a little bit too simple to be considered interesting. So I think when people first came up with this setup, they looked at solutions of this type. Yes.
I see. Okay, maybe first I stop recording and then the people feel better to ask questions.
Please.